بسم الله الرحمن الرحيم. معاكم عمر المعمري من مجموعة الكيمياء، وأرحب بكم جميعا وشاكر على حضوركم في محاضرتنا السادسة للمجلس الكيميائي للدكتور حمد المعمري بعنوان الكيمياء الخضراء. وإيش هي الكيمياء الخضراء أو ما هي الكيمياء الخضراء؟ بعطيكم نبذة بسيطة عنها. هي فرع حديث من فروع الكيمياء بهدف أو تهدف إلى تقليل أو إنقاص الانبعاثات الناتجة من عمليات التصنيع الكيميائي إلى أقل مدى ممكن، وتهدف إلى ابتكار مواد كيماوية جديدة تساعدنا إن نتخلص أو إن نحافظ على بيئتنا. طبعا بداية الكيمياء الخضراء في الولايات المتحدة عام 1990 بعد توقيع قانون منع التلوث، وفعلوا ذلك لتخفيف الانبعاثات الضارة وبالخصوص البلاستيك. مثل ما تعرفوا أنه يأخذ البلاستيك يعني وقت كبير جدا للتحلل. الحين بعرفكم على ضيفنا اليوم الدكتور حمد، دكتور غني عن التعريف، قدم أكثر من محاضرة معنا جزاه الله خير. دكتور ملهم وحياته حافلة بالمحافل والإنجازات التي يشاد لها بالبنان. يعتبر الدكتور حمد من مخرجات جامعة السلطان قابوس من قسم الكيمياء. تخرج عام 1996، أكمل الماستر في جامعة كاليفورنيا. إضافة إلى ذلك أنه حصل على شهادة الدكتوراه من جامعة أكسفورد عام 2006. بعد حصوله على شهادة الدكتوراه، الدكتور حمد زار العديد من الدول مثل ألمانيا واليابان. باختصار شديد يعني مسيرة الدكتور حمد ما شاء الله مسيرة علمية ناجحة، ومع قناة في اليوتيوب يعني تعد مرجع أساسي لطلاب الأورجانيك. بنضعها لكم تحت البوست المحاضرة لاحقا. الدكتور حمد هو اللي بيتعمق في الموضوع أكثر. تفضل الدكتور، المايك معك.
Good afternoon. Assalamu alaikum. Thank you to all of you. Thank you to the organizers of the Chemistry Society. I hope you can see the screen. So if anyone could confirm that you can see it, yeah, please.
Yeah, I can see.
Okay. So the title of the lecture today is Green Chemistry. I will try my best to give you a summary, if you like, of this fascinating new branch of chemistry, as Omar said at the introduction. So in the lecture today, I will give you a reminder of what chemistry is about, and then we'll talk about the concept of green chemistry. Of course, there is also green science, yeah. So we'll talk about green chemistry, what makes chemistry green, or what makes, as Omar said, some modern green chemistry different from the traditional or classical chemistry, if you like. So the title of the lecture today is Green Chemistry. We will try to learn a little bit more about this branch of modern chemistry, if you like, as Omar said in the introduction. So in the lecture today, I will give you a reminder of what chemistry is about, and then we'll talk about green chemistry, what makes what makes certain chemistry or certain chemical route, if you like, green, or what makes it different from the classical or traditional routes or reactions, if you like. And then we'll see green chemistry principles. And in the lecture today, I will not talk about all of the principles of green chemistry in details, obviously, because of the time. But I will talk about, as the seminar outline shows, about the very important green chemistry principle, which is atom economy. And then we'll talk about waste, what makes waste waste, if you like, how to reduce waste, how to deal with waste. Okay, and then we'll see catalysis, a very important, again, green chemistry principle, the definition of a catalyst, why is catalysis important, yeah, and the types of catalysis as well. And then we'll talk about solvents. We'll see that not all solvents are green. Some solvents are recommended because they are environmentally benign or friendly. Some solvents are not recommended. Again, connected with this is obviously the protection of the atmosphere. And then we'll see briefly different types of renewable resources as sources of fuel. As you know, nowadays we rely still chiefly on oil. We'll see different types of resources or sources, renewable sources of energy, not only energy, but also chemicals to manufacture chemicals. And at the end, we'll try to reach some concluding remarks. Okay, so let's begin of the definition of chemistry. And I'm sure some of you are chemistry majors or at least generally science majors. So you've taken chemistry at the university level. You've taken chemistry even in school, yeah. So if somebody asks you, how do you define chemistry? I'm sure a lot of you will come with all kinds of definitions. So if you say it is the science of chemicals or science of substances, materials, for example, compounds, okay, that's of course correct. If you say it is a study of chemical properties of substances, that's also acceptable. But again, as I always stress on in my lectures, either in person at the university or in the YouTube channel, or even in the last lecture which I gave to the Chemistry Society, chemistry, or the essence of chemistry, is actually formation of bonds, okay? That is what chemistry is about, formation of bonds, yeah, like carbon-carbon bond, for example, yeah? Carbon-oxygen bond or carbon-nitrogen bond. And what's concomitant with formation of bonds is also breakage of bonds. So some bonds break in reactions, some bonds form. That's actually what chemistry in essence is about, yeah? So it is about chemical reactions, it is about breakage of bonds, it is about formation of bonds. So of course, every bond requires 2 electrons, yeah, whether, regardless of the type of bond, whether it's covalent or ionic, as you know, 2 electrons are always needed. So chemistry is based on electrons. So some, as you know, some atoms lose electrons, some atoms gain electrons, depending on the metallic character of the atoms. Of course, the vast majority of elements in the periodic table or in nature are metals. Yeah, metals tend to lose electrons to form positively charged cations. Okay, so and why do they lose? They lose because it is easier for them to lose than gain. Non-metals, on the other hand, gain electrons, yeah, and they do gain electrons because it is easier for them to gain than lose. And how many electrons are gained or lost? Well, that will depend on what's called the valence electron. Yeah. Okay, so metals lose a number of valence electrons that are basically valence electrons, electrons located in the outermost shell, or the electrons responsible for reactivity. If you take sodium, for example, sodium loses 1 electron because it has 1 electron only in the outermost shell, and that's why sodium loses 1 electron. Magnesium, for example, loses 2 electrons. That's because it has 2 electrons in its last shell. So that's why magnesium loses 2 electrons. Non-metals, when they gain electrons, of course, they make anions. Metals, when they lose electrons, they make cations. Okay, and why does, for example, sodium lose 1 electron, or magnesium or calcium lose 2 electrons? That's because the electronic configuration of the number of electrons after the loss is the same number of electrons as a noble gas. Okay, and a noble gas is unreactive because its orbitals are completely full. So that's basically what atoms try to do, is they try to achieve a noble gas core. Okay, as I said before, okay, and as we always say, you don't eat indefinitely. Yeah? Everything has capacity. Yeah, يعني ما تاكلوا على طول ولا تشربوا 24 ساعة. يعني اوكي الواحد يشرب عشان يتخلص من العطش, for example, or ياكل عشان يتخلص من الجوع. Yeah, there is a limit. يعني, and that's exactly the same with atoms. Yeah. They lose a number of electrons, or they gain a number of electrons, depending on the number of electrons that will take them closer to the nearest noble gas. Okay, and again, gain or loss, that will depend on which is better or easier for the atom to do. Whether it gains or loses, that will depend on the distance between that specific atom in the periodic table and the nearest noble gas. Yeah. Okay. If a metal loses electrons, okay, it forms cations. If a non-metal gains electrons, it makes anions, and cations and anions can interact to form an ionic bond. There are non-metals, of course, as you know. So there's, of course, there are metals, non-metals, metalloids. Yeah, metals lose, they form cations. Non-metals gain, they form anions. Okay, and there are metalloids with they can do both. Now, if the bond is between a metal and a non-metal, yeah, okay, generally there are of course details. Okay, the bond will be ionic. If the bond is between two non-metals, the bond will be covalent, and that's when electrons are shared, not gains or lost, but shared. Okay, covalent bonding, and that's basically the heart of organic chemistry. So we see chemicals all around us. To appreciate green chemistry, by the way, we need to see if we actually encounter chemicals. Do we see them? Do we meet them, if you like? Do we use them? Do we eat them? Okay, do we inhale them or exhale them? Okay, and the fact is, chemicals are all around us. Yeah, okay, and organic chemistry is at the heart of this, by the way. Okay, because all the chemicals that we take as medicines, as you see in the slide that is shown, all of these painkillers contain, all of these painkillers are actually organic compounds. Yeah, so we see them. Okay, you see like phenyl salicylate, you see phenacetin, for example, ibuprofen. All of these are chemicals that are, or medicines, if you like, that are used to kill pain. Okay, like headache, for example. Yeah. Okay, not only these, there are of course other antibiotics. There are medicines for all kinds of problems, you know, medical or health issues or health problems, if you like heart diseases and all kinds of cancer, all kinds of other diseases. And of course, there are thousands, if not millions, of compounds that are now present in the as medicinal compounds, if you like. Yeah. So we take chemicals in the form of medicines. That's the conclusion now. Okay. Not only we take them as medicines, but also we encounter them in transportation. Yeah. So for example, when you drive a car, you fuel it. Yeah. You go to a petrol station, you fill it up with fuel or gasoline. Yeah. There are some cars or vehicles which depend on diesel. So again, diesel and gasoline are actually chemicals. Yeah. And there are also additives that are added to fuel. Okay, and even in catalytic converters in cars or other vehicles, okay, there are also chemicals in them. And of course, as Omar said, plastic waste is a major environmental issue. Okay, so plastic is actually a chemical. Yeah, so we see chemicals all around us. You see gasoline, for example, is a mixture of hydrocarbons, whether they are alkanes or alkenes. Examples of the structures that are shown here. So 75% of diesel also is also saturated hydrocarbons. And again, as you notice, these are all organic compounds. Okay, so why do we do this? Just for us to appreciate or acknowledge that we actually see chemicals and encounter them in our daily lives. Yeah, not only in transportation and in medicine, but also in clothing. Yeah, so if you see clothes, for example, they consist of fibers such as nylon. Okay, and there are two types of nylon that are shown. Yeah, and also in sport. Yeah, so we see chemicals in sport. For example, tennis rackets. You hear, for example, of titanium tennis rackets. That's because they are light in weight. Helmet also, they are made from polycarbonates. That's in car safety. Okay, again, another aspect, if you like, where chemicals are encountered. Yeah. Okay. Chemicals are found in food. Okay. If you have a refrigerator in your house, and these are examples of refrigerants. Yeah. Halogenated compounds that contain carbon X bond or like carbon fluorine or carbon chlorine bonds. And examples are the structures that are shown as refrigerants, if you like, that are used in refrigerators. Yeah. If la samah Allah, you have to go to the hospital, for example, to undergo a medical surgery, then the medical doctor will inject an anesthetic before the medical operation, yeah, or قبل العملية, if you want, yeah, مخدر يعني, yeah, okay. Anesthetics are actually organic compounds. Okay? So you see the examples in front of you, like this trichloromethane and an ether, and then another ether, and there are other compounds, okay, generally halogenated compounds or halogenated ethers, if you like, even, yeah. So examples of additional chemicals or organic compounds that are used, yeah. And now, you know, of course, since we are in this coronavirus pandemic, yeah, okay, you hear of all kinds of possible vaccines or cures for, if you like, for coronavirus. All of these are obviously organic compounds, yeah, okay. We see esters or organic compounds in fruits as well, yeah. Okay, so this slide shows the different esters in different types of fruits. For example, the first one, isoamyl acetate in banana, octyl acetate in orange, and so on. Okay, the point here is we also encounter chemicals in food, if you like, yeah. And these esters, by the way, and other esters are used in perfumery or fragrances industry, by the way, yeah, because they smell nice, yeah. They have very nice smell, so they are used to make perfumes, if you like, or perfumery. Yeah. So now, if we talk more about green chemistry, before we talk about green chemistry, we've seen, yeah, that we actually encounter chemicals around us. Yeah, we eat them. Okay, we, if you like, you wear them. Yeah, if you go to the medicine, you take them as a medicine, and so on, as we've seen. Yeah, and of course, you use them as a fuel to drive your car. So we talked about chemistry. Yeah, okay, it's the chemistry of bond formation, the chemistry of bond breakage. If you like, it's the science that deals with the properties of chemicals or substances. Okay, what about green chemistry? So what makes chemistry green, and what makes other chemistry not green? Yeah, so a green chemistry is a chemistry, if you like, it could be a chemical reaction, by the way. It could be a synthetic route where benefits are maximized and negative impact is minimized. Yeah, benefit, which means the yield of a product is high and the product is useful for human use. Okay, negative impact is minimized, which means waste is reduced, hazard is reduced as well. Okay, so in summary, if you like, or a concise definition of green chemistry is a practice of a science practice that aims at maximizing benefits in chemical processes in general. Yeah, chemical processes or chemical reactions at maximizing benefits and also minimizing the negative effects. What is greatly connected with green chemistry or green science, by the way. We can apply this, by the way, green chemistry definition even to science as a whole. Yeah, so you could say even that green science is a science that same thing, that maximizes benefits and minimizes negative impact. Okay, what's connected with green chemistry is a very important term which is sustainability. يعني الاستدامة بالعربي. Okay, which means meeting the needs of the current or present generation, and also not compromising the needs of the future generation. Yeah, so we don't want a method, okay, that works only now or only for 1 year or 2 years, but it does not work after 5 or 10 years. If anything that does, if a process that works now but does not work after 5 years, then it's not sustainable. Yeah. The same thing applies even to other fields, even law. Yeah. So if you have a law, for example, that works and functions well now, but it doesn't function 5 years from now, then it is not sustainable. So sustainability is meeting the needs of the present generation and also not compromising needs of future generation. A very important discussion of green chemistry, whenever green chemistry is talked about, is what is the green chemistry principles. Yeah, and there are 12 green chemistry principles that all of us, all people, all scientists, or all chemists who are interested in green science or green chemistry in particular to learn. Yeah. And try to understand. The first green chemistry principle is prevention. الوقاية خير من العلاج. Okay, so it is better to prevent than deal with. Okay, it's better to prevent waste, for example, than deal with it. Why treat a waste if we can prevent it from the beginning? Yeah, to start with. Yeah. Okay, so prevention, okay, is better than a cure, as they say. Yeah, الوقاية خير من العلاج. Yeah. Okay. Again, remember, green chemistry deals with chemical reactions. Yeah, so there is waste in chemical reactions. We try to minimize waste. So if we can prevent waste from the beginning, okay, why deal with it? Yeah, so that's the meaning of this first principle. Second principle, which is extremely important, is atom economy. So atom economy may sound to be new to you, yeah, okay. So you hear of economy like in finance, for example, yeah, or commerce, yeah. But maybe you have not heard of atom economy. So what does that mean? Well, atom economy, if you have a reaction, yeah, a reaction employs reactants, yeah. Every reactant is a molecule. It's a chemical, yeah. Every molecule comprises atoms, yeah. So the reactants that contain atoms react and they give products. Yes, it could be one product or two products. If all atoms in the reactants are incorporated in a single product or products in general, then the reaction is atom economical, which means there is no waste. Yeah. If not all atoms are converted into a product, then atoms will be wasted. Yeah. So there is waste. Or byproduct. That type of reaction, if you like, is not atom economical. Yeah. Okay, I will talk more about this, okay, in the coming slides. The third green chemistry principle is employing less hazardous chemical synthesis. You see, chemical roots have chemical reactions. Yeah, chemical reactions employ reactants. Okay, they could employ as well reagents. They could employ additives. Yeah. Okay, the chemical synthesis that employs generally or relatively less hazardous chemical compounds or chemical reactants, then that is preferred. Okay, it is green. A chemical reaction that deals with toxic substances, for example, or hazardous materials or substances is not green. Also, The same thing applies to not only to reactants, but also to products. Yeah. If a product of a certain chemical reaction is toxic or it is hazardous, then that reaction is not green. If a chemical reaction produces a product which is safe or environmentally benign, then it is a green chemical reaction or a green synthesis. Yeah. So the idea here is to avoid hazardous or toxic materials or substances, whether they are reactants or products or even additives, yeah, okay, or even catalysts, yeah, okay. We try to make all participants, if you like, in reactions green or environmentally benign. The fourth principle is designing safer chemicals, yeah. What does that mean? What this means, if you have an option, okay, between two chemicals, maybe both chemicals can cure a disease, yeah. Both of them work, yeah, but one of them is toxic and the other is not toxic, okay. So you would prefer, of course, the one that is not toxic, okay? And that is green, but the other one is not green. This applies to anything, okay. It could be a chemical reaction in the lab. It could be a material of some use. It could be a substance of other uses in life, yeah. Okay, the products should be designed as much as possible so that their toxicity is minimized. The fifth principle, or the fifth green chemistry principle, is the use of safer solvents and auxiliaries. As you see, chemical reactions generally, not always, they employ solvents, yeah. Okay, not all solvents are safe, by the way. Some solvents are not environmentally benign, as you will see. Okay, so green chemistry targets safer solvents that are environmentally benign or that do not end up in the atmosphere. Yeah, if the solvent is volatile and it's not environmentally benign, it will be harmful to the environment, obviously. Yeah? So green chemistry deals with the use of safer solvents as much as possible, and also auxiliaries. Auxiliaries are basically additives or materials, okay, that are used in chemical reactions or even later in workup or purification steps. Okay, the practice or the procedure that deals with safer auxiliaries are preferred because these practices are considered green. A sixth green chemistry principle is design of energy efficiency. Of course, when we do a chemical reaction, yeah, okay, we can either do it at room temperature, as you know, or we do it at reflux, or even at sub-zero temperatures, yeah, okay, and we stir, you know, using the magnetic stirrer, or you heat using a hot plate, yeah. So there is consumption of energy, yeah. Okay, so a green reaction is a reaction with normal temperature or room temperature. So room temperature is preferred. Higher temperatures will require energy consumption. The seventh principle is the use of renewable feedstocks. Yeah. Okay, there are materials which can be obtained from nature, by the way. There are chemicals that you'll see also coming up, okay, that can be obtained from nature. You don't have to make them, you don't have to synthesize them, but you can make them from renewable resources. The eighth principle is to reduce derivatives. It is better for a chemical route to be as short as possible, yeah. And it is better, and for the route to be as short as possible, okay, it is better if it avoids derivatization, yeah. Okay, like protecting groups, if you know protecting groups, yeah. Okay, a protecting group, you put it on before a chemical reaction, and then you do the chemical reaction, and then you take it off. If there's no need, okay, you see, so there's two additional steps, yeah. Putting in the group and then taking it off, yeah. So two additional steps. If we can avoid these two additional steps, that's actually better, because every step requires chemicals. Every step requires additives. Every step usually requires a solvent, yeah. Okay, every step requires stirring, maybe heating, so there's energy consumption, yeah. So the route which consists of the least number of steps is considered green. Catalysis. There are reagents, okay, if you react a chemical A Will chemical be you use a reagent? It's not quite a reactant, but it could be a reagent or an additive. Yeah. Okay. If that reagent is used in, if you use reactant A as 1 mole, yeah, you're familiar with the mole, of course. Yeah. That's the SI unit for the amount of substance. Yeah. Okay. If you use 1 mole of reactant A and 1 mole of reactant B, and then you use 1 mole of the reagent, then that reagent is not considered a catalyst because it is used in stoichiometric amount. If we can reduce the amount of that reagent to less than 1 mole, then it would be described as a catalyst. And of course, a catalyst by definition, as you know from school even, yeah, is a material or a substance that speeds up chemical reactions without getting consumed. We'll talk more about catalysis, that's coming up. Design for degradation. Design for degradation means that products that are obtained at the end of a reaction are preferably designed so that they don't persist in the environment. Yeah. Okay. Persistence in the environment, as you see, is a result of strong bonds. Yeah. We don't want to target strong bonds. Also, we don't want, on the other hand, yeah, to target weak bonds. So weak bonds are not should not be targeted. Strong bonds should not also be targeted, because weak bonds can break, and they can break. If they break, they can explode, by the way. Yeah? That's explosives now. If the bond is strong, that bond can persist in the environment. Yeah, like plastic. Yeah, okay, plastic. Yeah, contains strong bonds. Okay, so we try to avoid materials that has strong bonds like plastic. Okay, okay. So degradation basically, or materials that have bonds that cannot break or degrade, if you like. Yeah. So we'll see there are rules for this, or guidelines as well. The 11th green chemistry principle is the prevention of pollution. Yeah. So the chemistry that minimizes pollution, or that don't emit toxic or hazardous materials in the atmosphere, is green. Yeah. Yeah. Also, not only we try to avoid pollution, we try to avoid accidents, as green chemistry number 12 says. Yeah. Okay. So a chemistry that prevents accidents is also green. Okay. That's actually a green chemistry principle. We don't want accidents. We don't want fires. Yeah. We don't want to kill ourselves simply because we are doing chemical reactions. We don't want to harm others. Yeah. Okay. So that's the 12th green chemistry principle, and it is the last one. Now I will talk about some details of selected green chemistry principles, as I mentioned in the first one is atom economy. And atom economy, as concisely mentioned a while ago, it is incorporation of all atoms in reactants in a single desired product. So again, if you have reactant, just to make it clearer, if you have this hypothetical reaction which is in front of you, R1 plus R2, R is a reactant, yeah, 1 is 1, yeah. So R1, reactant 1, and reactant 2 react to give a product, and U. P stands for a product. U stands for unwanted or a high product. So the definition or the explanation or the meaning of atom economy is that all atoms in R1 and all atoms in R2 are converted to P. All atoms in R1 and R2 are converted into P, which means no atoms are lost. No atoms are lost, which means that U will be what? I'm sure you can predict it, yeah. U in that case will be 0. If all atoms in R1 and R2 are converted into P, then U is 0, which means if U is 0, or there is no byproduct or no unwanted product, this means the reaction is of total atom economy or 100% atom economy. If U is not 0, which means some atoms from either R1 R2 or both, if atoms from R1, R2 or both have been wasted in the form of U or of a byproduct, then the reaction is not atom economical, or not totally atom economical. And atom economy, by the way, is calculated. Okay, it's coming up. Okay, I'm giving you examples of totally atom economical reactions. Yeah. So how to calculate the percent at what's called the percent atom economy is to balance the chemical equation, of course, first. Yeah, and then we divide the molecular weight of the desired product times the number of moles, of course, by the balanced chemical equation. You divide it by the molecular weight of all reactants. So you see a desired product, so one product basically, and you divide it by you divide its molecular weight by the molecular weight of all reactants. So all economy and atom economy deals with incorporation of all atoms in reactants like R1 and R2 in the hypothetical reaction in front of you into a single desired product P, which means if all atoms in R1 and R2 are converted into P, then U, which is unwanted, or a byproduct, is actually 0, which means if U is 0, then the reaction of 100% atom economy or of total percent or total atom economy. Now, if some atoms from R1, R2, or both are not converted into P, or if they are converted into a byproduct or U, this means that U is not 0, which means that the reaction is not of 100% atom economy. Okay, so it's a very important term. It's one of the 12 green chemistry principles, yeah. And we can easily calculate it as shown here, and we will calculate it for one reaction or two that are coming up. As you know, also from school and also from your university chemistry, there is also percent yield, yeah. Okay, and percent yield, as you remember, even from basic chemistry, it is actual yield or experimental yield divided by the theoretical yield, yeah. And if you remember, okay, the calculation of percent yield depends on the limiting reagent, yeah. Okay, now that percent yield is totally different from the percent atom economy. So it is very important not to mix the two, yeah. Percent atom economy, it is totally different from the percent yield. The atom economy or the percent atom economy takes into account byproducts or unwanted products. Now, the percent yield takes into account basically the yield calculation based on the limiting reagent, yeah? So they are different, yeah? And as you will see, it's coming up that we could have a reaction which is of 100% yield, but not total percent. Okay, so this scheme shows a reaction in general, which is less than 100% yield and also less than 100% economy. And remember, atom economy deals with incorporation of all atoms in all reactants in a single desired product, which means if there is a byproduct, it is not totally atom economical. If there is a byproduct, it is, if there is no byproduct, it is totally atom economical. And if there is a byproduct, then the reaction is of less than 100% atom economy. If you take this hypothetical scheme, reactants to give products using a specific reaction, yeah? So you see here, there are byproducts from desired reactions. So there is desired reaction, obviously, that leads to the products from the reactants, yeah? If there are byproducts, this means the percent atom economy is less than 100%, yeah? Or the reaction is not totally atom economical. The reaction could be incomplete. So if the reaction does not go to completion, then there are recovered starting materials, which means that the percent yield will not be 100%, yeah. Okay, there could be also a side reaction. If there is a side reaction, the percent yield cannot be 100% because there is a side reaction. And that side reaction may even lead to other byproducts from that side reaction. So this is an example of a reaction in general with less than 100% atom economy and also less than 100% yield, less than 100% yield because there is a side reaction, and less than 100% atom economy, that's because there are byproducts. This is an example now of a reaction in general, or a scenario, if you like, of a hypothetical scheme or reaction that is 100% yield, yeah, but less than 100% atom economy. So if you remember the previous slide, there was a side reaction. Yeah, if we go back, so there was side reaction. Now there is no side reaction, yeah, which means the yield could be 100%. But still, there are byproducts. If there are byproducts, this means that percent atom economy cannot be 100%, yeah, or the reaction cannot be of total atom economy. So this is an example again of a reaction that could be of 100% yield because there is no side reaction, no undesired side reaction, but also it is of less than 100% atom economy because there are byproducts or there is waste. The green reaction, yeah, that's what green chemistry is about now. Okay, the reaction of 100% atom economy, which means all atoms, again, if you remember that equation 2 or 3 slides ago, if all atoms in all reactants are converted or end up in a single desired product, then this means the reaction of 100% atom economy. So which means obviously no side reaction, yeah, and obviously no byproducts. So if there is no byproducts, the reaction is of 100% atom economy, and if there is no side reaction, the percent could be of 100% yield. So the question is, how do we know this? Can we know this in general in the planning stage of reactions? Yeah, if we have a compound, for example, that we want to make for medical purposes, yeah, يعني دواء مثلا, yeah, that we want to make, okay, well, مبيد حشري ولا whatever it is, yeah, agricultural substance, okay, that's needed, or even a chemical that's needed for biological reasons, yeah. Okay, if we have to make a compound, can we predict if the synthesis will be atom economical? Well, the answer is generally yes. Yeah, some reactions are known to be of 100% atom economy, like addition and rearrangement. Yeah, okay. So you see this in our organic chemistry, but organic chemistry is very strongly and greatly linked with green. So addition and rearrangement, organic reactions are types of reactions that are of 100% atom economy. And as you learn in basic organic chemistry, that alkenes undergo addition reactions when they react with electrophiles. Yeah. So this reaction that is shown is an example of addition reaction between the alkene that is shown and HBr to give the product. Yeah. Okay. Now, the meaning of atom economy here, or the percent atom economy, is to see if all atoms in the first reactant, the alkene, and all atoms in the second reactant, which is HBr, if all atoms end up in the single desired product shown. Let's see that. Without any calculation, by the way, you can do this by inspection to determine if the reaction is 100% atom economy or not. Yeah. So you see this benzene ring, it's a phenyl group, obviously, with this carbon double bond. You see, you have all carbon atoms here. This first carbon of the alkene has 2 hydrogens, and this carbon, there are still 2 hydrogens. This carbon, the second carbon in the alkene, it has 1 hydrogen, and that second carbon in the product has also 1 hydrogen, which means all atoms in the alkene, carbon and hydrogen atoms, end up in the product. Look, if you look at HBr, 1 H from HBr bonded with the first carbon in the alkenes. That's why now there are 3 hydrogens in the product. So this hydrogen from HBr is not wasted. Br from HBr has also been incorporated in the product, which means Br from HBr has not been wasted either. So both atoms of HBr, hydrogen and bromine, ended up in the product, which already has the alkene unit, if you like, yeah, which means all atoms in both reactants end up in a single desired product. If we want to calculate the So this means that this reaction is of 100% atomic economy, definitely, yeah? Because all atoms, again, in both reactants end up in a single desired product. Now, if we want to do the calculation, yeah, you have to balance the chemical equation. That's always, by the way, always the first step. Whenever you want to do any calculation, whether it is stoichiometric or calculation of atomic economy, we have to balance the chemical equation, yeah? Okay, if we take the molecular weight of the product, you multiply by the number of moles as determined by the balanced chemical equation. Of course, it's 1, 1, 1 always, yeah, so 1 to 1 to give 1. So 1 mole of the alkene reacts with 1 mole of HBr to give 1 mole of the product. Yeah, you multiply 1 by the molecular weight of the product, and you divide it by the number of moles of the alkene times its molecular weight plus the number of moles of HBr as determined by the balanced chemical equation times the molecular weight, and then you multiply by 100, you get the result. And if you do that, you can double check the calculation yourself, even at home, or even now if you wish, I'm sure you will get 100%, which means that the percent atomic economy of this addition reaction is 100%. Addition and rearrangement are types of reactions that are of 100% atomic economy, but substitution and elimination are other organic reactions that are of not total atomic economy, which means the atomic economy of substitution and elimination reactions are not 100%. This is an example of a substitution reaction in front of you, reaction between the alcohol and phosphorus tribromide to give the bromide shown, yeah, okay? And you see immediately that there is already a byproduct, okay? The moment there is a byproduct, immediately the reaction is not of 100% atomic economy, yeah, without any calculation, yeah. But the calculation can be very important, by the way, if you have two substitution reactions which can lead to the same product, or maybe a substitution and elimination that can lead to the same product, and you want to select between them, yeah. So to choose between them or to select between them, the good practice to do the calculation of the percent atomic economy. If you calculate the percent atomic economy of this substitution reaction, it will be 87%. Yeah, that's always, and always, as I said before, we have to balance the chemical equation, yeah? Because no calculation is correct if the equation is not balanced, yeah? So you balance the chemical equation, 3 moles of the alcohol react with 1 mole of phosphorus tribromide to give 3 moles of the product and 1 mole of the byproduct shown, okay? If you do the calculation as before, the result will be 87%, which means this substitution reaction, just like any substitution reaction, by the way, this substitution reaction does not or is not associated with 100% atom economy. Now we are about to tackle another green chemistry principle, which is waste. So waste is, by the way, is implied in many green chemistry principles, of the 12 principles of green chemistry. And the first green chemistry principles with which waste is connected is prevention. Yeah, الوقاية خير من العلاج, if you remember. Yeah, okay. So it is better to prevent waste than deal with it. Okay, it's better to do prevention, تعملوا وقاية if you want, بدل العلاج if you want. Okay, يعني ما في داعي الواحد يرمي نفسه إلى التهلكة إذا ما في داعي, مثل ما what makes waste a waste, what makes a waste waste, for example. Yeah, so waste by definition is a material, if you like, or a substance that is not desired or discarded. Yeah, it is a substance. It could be generated, by the way, at the end of the chemical step or a chemical reaction. If there is a substance at the end of a chemical reaction that is not desired or disposed of or discarded, it is considered waste. Okay, the green chemistry principle that's linked with waste is prevention. Now, there is a hierarchy, if you like, or steps that deals with minimization of waste. And the first step is reduction at source. Yeah, as if you see the step at the top, it is better to reduce waste at source, which means if you have a chemical reaction, yeah, you design it to be not wasteful, which means a reaction like addition, yeah. Addition reaction, for example, does not give waste. Substitution, for example, leads to waste, yeah. So if you have a choice between addition and substitution, you should go for addition if both reactions, of course, will lead to the same product. If reduction at source is not possible, then the next step would be to reuse. So better to reuse than deal with it. Yeah, if you have a waste at the end of a chemical reaction, if you can reuse it, that's actually green. Yeah, better than waste it. Yeah, or even deal with it. Yeah. If you cannot reuse, then the third step will be to recycle. And recycling means to recover, basically. You can recycle a material in order to recover it or to recover even energy. Yeah? Okay. And if you cannot reuse, if you cannot recycle, then we can dispose of. So disposal is really the last resort or the last step in this hierarchy, if you like, or in the procedure in dealing with waste. So the first step always is to reduce at source. If we cannot reduce at source, then reuse. If we cannot reuse, then recycle. If you cannot recycle, then deal with or treat or dispose of. This is an example for two methods to manufacture phenol. Phenol, of course, is a bulk chemical that's important industrially. Yeah? Okay, and there are two methods to make phenol. One method is the one that is shown in front of you. So starting from benzene and ending up with phenol. So the first step is sulfonation. The second step is the reaction between sodium carbonate with benzene sulfonic acid, and so on. Yeah. So there are 4 steps, and if you see step 1 has the product that is desired and water. Water is not, although it is a byproduct, but it is a green waste, if you like. Yeah. Because it is water. Yeah. Okay. The second step produces carbon dioxide and water. So carbon dioxide is waste. Every waste is labeled in red, by the way, and in a box as shown. Yeah. So carbon dioxide, sodium sulfite, and sodium hydrogen sulfate are the three types of waste in this route of the production of phenol. Now there is another route. Okay, that's called the cumene route to phenol. So the same product, by the way, phenol, but a different route. So this route consists of basically 3 steps. Yeah. So again, starting from benzene and ending up with the product. And you see, the first step employs what's called zeolite. Zeolite, by the way, is a catalyst. So there is catalysis. Yeah. Okay, and the last step also deals with employs a catalyst. Yeah, so 3 steps only here, and this route or this method employs catalysis, and catalyst, of course, reduces waste. Yeah, so this route is considered green because it's not as long as the first one that you saw before, and not only that, the percent yield or the yield of the final product in this route is 90%, which is high. Yeah. So that's why the benzene sulfonation route, which you saw before, became obsolete or not used anymore. This is another example of a wasteful synthesis and not so wasteful synthesis. Ibuprofen, the product in the box that is shown, is a painkiller. If you remember the scheme or the figure that I showed you a while ago at the beginning of the lecture of painkillers, you would have seen ibuprofen. Ibuprofen can be made through this route. Okay, you don't have to worry about the details. Yeah, but again, the waste is shown in red. Yeah, so every time you see waste at the end of a chemical step. So there's 1, 2, 3, and 4 actually also. Yeah, so there are 4 types or 4 wastes in this route. Yeah, this is the original method for the synthesis of ibuprofen that's used by Boots, by the way. Now, there's a new method, okay? There's a new method to manufacture ibuprofen And the new method employs only 3 steps. Yeah, the first step with HF, second, which is a catalyst, by the way. Yeah. Okay, and the second step, also Raney nickel in the hydrogenation reaction. This is also a catalyst. Yeah, and carbon monoxide and palladium. These are also catalysts. Yeah. So 3 steps only, and the 3 steps employ catalysts. All of them employ catalysts, and there is only one waste, which is acetic acid. Unlike before, if you again we go back before to the previous original synthesis, okay, you will see 4 types of waste. This time here, only 1 type, and this route employs catalysis in the 3 steps of the reaction. So less number of steps, less waste, catalysis here, okay, and the HF, okay, which is used as a catalyst, replaces aluminum chloride that you saw before, which was used in stoichiometric amounts. So therefore, this method or this route is definitely better than the previous one. This is therefore a green chemical synthesis in comparison with the previous one. A very important concept here, or topic, if you like, when we talk about waste, is the cost of waste. Yeah, because as you see, some waste has to be dealt with. Okay, there are all types of waste treatment. If we cannot design a reaction that is totally atom economical, and if we cannot reuse or recycle, then we have to deal with the waste. And it could be a toxic waste, by the way. It could be a chemical waste, it could be a biological waste, and there are all types of waste, and there are different types of treatments that are also coming up. Okay, the treatment of waste can be costly. The treatment of waste can be costly. So there is a performance indicator that's called the triple bottom line that is used to judge performance of companies, including chemical companies. Yeah. So basically, to see if they have waste, okay, then the performance is not great. If the waste is less, then performance is better. That's in simple terms. Yeah. Okay, this principle, okay, that's called the triple bottom line, was established by somebody called John Elkington. Okay, and it consists of 3 pillars or 3 strands: social, environmental, and economical. The idea is for the company, for it to be judged a great company, is not to produce waste. Yeah. And for the company to make profit, right? Because the company, like any industry, their aim is to make profit, and to make money, yeah? To make benefit, if you like, yeah. But also, shouldn't make waste, or they should at least make the least, or produce the least amount of waste. They should not harm the environment, obviously, and also they should not damage their reputation. Yeah. So that's the meaning of social. Okay. So I'm going to discuss now this in more details. You don't have to worry about the complexity of this chart that's in front of you, but the bottom line is that this triple bottom line, or TBL, is used to judge the performance of chemical companies. Okay, and the cost of waste will have a direct impact. The cost of waste will have a direct impact on the performance of the company. If the company is very wasteful, it will have to waste a lot of, it will have to deal with it, obviously. Yeah? So the direct disposal of waste at the bottom, in the center, at the bottom, okay, this will make the company invest a lot of money. Yeah, so it will be expensive for the company to deal with the waste. Okay, so that will be a burden. So it's not good for the company to produce waste, because waste is costly. And if you look at the environmental strand, every chemical reaction, like the manufacture of methanol in Salalah, for example, or polypropylene in Sohar, yeah, every chemical industry produces waste, yeah, yeah, but there is some waste, okay, that's generally described as authorized, and there is waste that's described as unauthorized, yeah. So if you look at the left side, the environmental, yeah, you see authorized emissions and unauthorized emissions, yeah. Yeah, the authorized emissions will reflect the public attitude. How do the public view the company? Yeah, is it good or not good? So, which means if there is emission of gases, for example, yeah, toxic gases in the area where the chemical company is, okay, then that will not be good, okay, for the company, because their reputation will not be good, because people will not view them highly, yeah, okay? And if there is unauthorized emissions, this means there should be fines, you know, for such unauthorized emissions. And again, here, the government role or legislation is very important in this regard to impose fines, يعني عقوبات, if you want, yeah, for any chemical company, لأي شركة, for example, that produces unauthorized emission, you know, like toxic gases in the atmosphere. And not only that, okay, not only the company will lose money because they will be fined, yeah, by the government, for example, yeah, okay, or by any agency, yeah, environmental agency, they will have to do cleanup as well, yeah. So they should do the cleanup as a result of the emission, okay, but again, this will cost them money, and also the perception or the reputation of the company in the minds, yeah, of people will not be good, yeah, because of these unauthorized emissions. Now, if we talk about the social strand on the right side, for similar reasons, yeah, if a company produces waste that's not good for health, for example, yeah, or that affects human health adversely, or that affects animals, if you like, or plants, okay, then people will not perceive these companies highly. يعني بيفقدوا سمعتهم, if you like, yeah. يعني الشركة ولا المصنع بيفقد سمعته, if you want, if that company produces a waste that is harmful to humans, animals, or even plants, yeah. So the public will not view them highly. Not only that, by the way, as you know nowadays, okay, media is very, very active. Okay, the people will write about them, yeah, people will report about them in local media, whether written or seen, or even in social media, for example, yeah. If a company produces obnoxious or noxious gases, for example, or harmful or toxic substances, then the media or people will not leave them, yeah. So they will be reported, and then their image will be damaged, yeah. So سمعتهم again يعني بتنفقد. And when talking about the waste, it is very important to consider the volume of the waste, the nature of the waste, whether it's chemical, physical, or biological, and how much of it, yeah. Okay. And if there is solvents, for example, you know, at the end of that is used in a chemical reaction, and it is volatile, do we have to use that volatile solvent? Can we use a better solvent that's environmentally benign? Okay, more details are coming up when we talk about solvents, yeah. So solvents can be wasted, by the way. So it's better to, again, to minimize waste if possible. It is better if the reaction is high yielding. It is better if reactions are of 100% atom economy, because again, 100% atom economical reactions do not lead to byproducts. And not only in the reaction itself, but also in the workup. As you know, every chemical reaction has what's called a workup stage, yeah, or a purification stage, yeah. So there could be waste in every stage of a chemical reaction. And our aim here as scientists, or as modern green chemists or green chemists, is to minimize waste, yeah, to develop a green process, a green synthetic route toward a compound that is useful. Do we have to use organic solvents? Okay, because there are reactions which do not require a solvent, by the way. So if the answer is no, then why use an organic solvent? Because it could be that the solvent is not environmentally benign, or it could be that it is volatile, okay? Do we have to use protecting groups? As I mentioned, a protecting group is a group that you put on before a chemical reaction, and then you do the chemical reaction, and then you take it off in the third step. So there are 2 additional steps. If we can avoid these 2 additional steps, this is better, because the route will be shorter. Okay, there'll be minimization of materials, minimization of reagents, minimization of chemicals, minimization of reactants, minimization of additives, reagents, and also minimization of energy. If we use a reagent, can we use it as a catalyst? Okay, if the answer is no, then that's preferred. It is green. Yeah. And of course, there are other chemical considerations, okay, that you may be aware of, like selectivity and others, yeah, okay, which we don't have to worry about it. But of course, the reaction, which is very selective for a specific site in a chemical or a reactant, that's of course better, because the reaction will be more efficient in that case. And again, as we said before, yeah, it is better that the reaction is of total percent atom economy, which means there is no waste or byproducts. Yeah, okay, like what? Like addition and rearrangement reactions. Now I'll talk briefly about the treatment of waste, or actually even generally the types of waste, because of the time now we cannot talk about everything in details, obviously. Yeah. Green chemistry, by the way, is huge, yeah. And because there's organic green chemistry and there's analytical also, yeah, and there could be physical, yeah. So what I'm giving you in this lecture is a general or broad lecture in green chemistry. Yeah. And of course, as I mentioned before, organic chemistry really is at the heart of green chemistry. When you have waste, so if we have to have waste, again, remember, our goal is to not to have waste. Well, how? By using addition reactions, for example, because if you do an addition reaction, there is no waste. Yeah. Okay. But if we have to have a waste, okay, then we have to deal with it. Okay. There are all kinds of treatments, yeah, that depend on the nature of the waste, whether it's physical, chemical, or biological. The physical treatment basically deals with filtration, if you like, or refining waste, yeah, before you chemically treat it or before you biologically treat it, yeah. So separation basically is what this physical treatment is about. Chemical treatment, if you have a waste that you have to deal with it, then there are different types of chemical treatments that are possible. One of them is neutralization, for example. If you have an acid waste, yeah, you could neutralize it by reacting the acid with a base. If you have a base waste, for example, then you could react it with an acid in the treatment in order to neutralize it. So neutralization basically neutralizes acidic or basic waste. The second type of chemical treatment is oxidation, which converts waste into carbon dioxide and water. There is another type of oxidation, which is called wet air oxidation, for difficult materials, if you like, to deal with materials or chemicals that are not easy to oxidize using normal methods. Yeah. Okay, so if that's the case, then what's called wet air oxidation method is used. Okay, wet air oxidation employs sophisticated oxidizing agents, whereas oxidation uses normal oxidizing agents. Advanced oxidation processes is also another chemical treatment that is used when the two oxidation treatments before fail, basically. Yeah. Okay. So this method is used to treat maybe sequentially. So one step after another, and so on. So it's combination of oxidation steps, if you like. You deal with waste that's not easy or not possible to treat using a single oxidation step. There is also chemical reduction, which chemical reduction basically reduces substances into less toxic materials like metal ions. Yeah. So reduction, for example, of chromium 6 into chromium 3. Yeah. Chromium 6 is toxic. Yeah. Okay. So that's an example. Okay. The other example or the other type of chemical treatment is precipitation. If you have a metal ion in a waste, for example, at the end of the reaction, and it is toxic, yeah, okay, like chromium, for example, or cadmium, for example, and you want to remove that metal ion from the waste, then you add an anion to react with it, and when it reacts with it, it forms a precipitate, and when the precipitate is formed, then you can simply filter it, so you can remove the toxic metal ion by precipitation reaction. So there are different types of chemical treatments that can be done. Sometimes more than one type is done, by the way. Okay, maybe oxidation after neutralization, maybe chemical precipitation after oxidation, which is after neutralization. Yeah. So it is sometimes we have to use different types of chemical treatments in a single waste. Yeah, or in the treatment of a the design for degradation, this is also one of the 12 principles of green chemistry. We try to avoid persistence of chemicals in the atmosphere. Yeah, we try to avoid the problems of plastic, by the way. Okay, persistence when the compound has very strong bonds, then it cannot be degraded. Yeah, a compound with very strong bonds cannot biodegraded, or maybe it's difficult to degrade by chemical methods. Yeah. So it's better to prevent. Remember prevention, yeah, we can prevent waste, yeah. We can design also waste, yeah. If we have to have waste at the end of a chemical process, then better to design it, which means we try to use natural materials, yeah, as reactants. So use of natural materials will definitely produce waste that's easier to deal with, or a waste that could be degraded. We try to avoid aromatic compounds, because aromatic compounds, and especially the ones that do not contain groups in a 1-2 relationship, they are difficult to dispose of or difficult to degrade by chemical methods. Yeah. Electron withdrawing groups should be avoided, because electron withdrawing groups like the nitro group, for example, or the halogens, for example, yeah, they decrease degradation, or the rate of degradation. So it is better that a product does not have electron withdrawing groups if we don't have them. If we don't have to have them, yeah. Heterocycles should be avoided. Branches should be avoided, yeah, again, because straight chains are easier to degrade than branches. Ethers should be avoided, because ethers are inert functioning groups. Yeah, they don't react, or they cannot be disposed of or degraded by chemical methods easily. Strong bonds like carbon-fluorine bonds are very difficult to degrade, by the way. So this is in a way like plastic, yeah, in a way, yeah. So plastic that contains strong bonds, or strong bonds, or compounds that contain strong bonds should be avoided, by the way. Or if you have to design a compound or a product or a medicine, it is better that the medicine does not have that strong bond if there is no need for it. Of course, if you have to have it, or if a compound must have it for certain biological reasons, then of course that's a must. Yeah, then we cannot really do anything with it. Yeah, it's better that the compounds are water soluble. Yeah, so water soluble materials are recommended. Yeah. Okay, and materials or compounds of small molecular weights are also recommended. Okay, because then the degradation will be facilitated. So these are general guidelines for the design for degradation. Okay, if we have to synthesize a compound. We go to catalysis, another very important green chemistry principle. Okay, and catalysts, by the way, are materials or substances that are used in less than 1 mole. If all reactants are in a 1 mole, they are used in 1 mole, okay? So you balance the chemical equation. If a material is used in less than stoichiometric amount, it's called a catalyst. But a very important requirement of the catalyst that it should be regenerated, by the way. It should be generated first at the end of the reaction, and then also then it should be regenerated or recycled during the reaction. Yeah. And the catalyst should speed up the reaction rate, it should enhance the reaction rate, but it should not be consumed. Yeah. Okay. The idea is to make the reaction fast. The idea is to save energy, right? The idea is to minimize energy. Okay, that's green, yeah. And if you use a catalyst, by the way, waste is minimized, yeah. So waste is reduced if materials are used in catalytic amounts, yeah. Okay. Now the only negative aspect or drawback of catalysts is that usually they use metals, like heavy metals which are toxic, like cadmium, for example. Okay, but there are other types of catalysts that you will see which do not have metals. Yeah, so it could be a drawback for the catalysts that have metals, but it may not be a drawback if the catalyst does not have a metal. Okay, very important factors that determine the performance of catalyst is selectivity. You want a catalyst, by the way, that's efficient. Yeah? You don't want a catalyst that's not efficient. That's basically the bottom line really of this slide. So selectivity turnover frequency, and turnover number. Basically, you want the catalyst to produce as much as product from a reactant, to produce as much as product from a reactant. So the amount in moles of product that's produced, okay, is reflected per second is reflected in the what's called the turnover frequency per mole of the catalyst, obviously, whereas the amount of the product per mole of the catalyst is called the turnover number. We are talking about efficiency, remember, yeah? The catalyst should be as efficient as possible. There are two types of catalysts, as I'm sure some of you are aware of. There's a heterogeneous catalyst and there's a homogeneous catalyst. Heterogeneous catalyst, basically a catalyst that's not in the same reaction medium or the medium of the reaction. It's a different phase. Basically, it's insoluble, if you like. Yeah? Okay. The homogeneous catalyst or a homogeneous catalyst is a catalyst that is soluble, yeah, in the solvent of the reaction or in the reaction medium. And there are differences between them. Okay, you don't have to worry about the details. Okay, of this. Okay, I'll give you a summary of what the general or important features of heterogeneous catalysts. And the important feature of heterogeneous catalysis or catalyst is recovery. If you see here, it's readily available, readily separated. Yeah, you can separate a heterogeneous catalyst at the end of the reaction simply because it is heterogeneous. Yeah? Okay, simply because it is heterogeneous, which means it separates itself from the reaction mixture at the end of the reaction. That's actually good because we can filter the catalyst and then reuse it. Yeah, okay, or we can save it for future reuse. A very important feature, on the other hand, of homogeneous catalyst is the high reaction rate. Yeah. So here, a remarkable feature of heterogeneous catalyst is separation or recyclability, recovery or recyclability. A very important feature of homogeneous catalyst is the high reaction rate. Every type of catalyst, by the way, has a disadvantage. Okay. Okay, so there is an important feature of each type, and there is a drawback of each type. We cannot say always the heterogeneous catalysts are better simply because we recycle them, but they are less efficient than homogeneous catalysts, by the way. But homogeneous catalysts cannot be recycled. You see the difference, yeah? Heterogeneous catalysts can be recycled, homogeneous catalysts cannot be recycled. Homogeneous catalysts have higher reaction rate than heterogeneous catalysts. Yeah, so every type has its own advantages and disadvantages. The comparison is difficult. It's not easy to make generalization. It is not right. It's not wise to say that this type is green, the other type is not green, because as you see now, okay, each type has its own advantages and disadvantages. Yeah. So, but how do we select? Well, the choice will depend on the reaction itself. Yeah, the choice of which catalyst to use or which type to use will depend on the requirements of the chemical reaction or the requirement of the process or the situation, if you like. Yeah. So the best catalyst will be the catalyst that is recyclable. So basically, a catalyst that has the heterogeneous feature, and also the best catalyst will be a catalyst of high reaction rate, like homogeneous catalysts. Yeah. So if we can combine the recyclability and the high reaction rate, that will actually be green. Yeah. That will be an ideal catalyst. But as you know, ideal catalysts are difficult. Okay. If we go a little bit in more detail with what not really in details, yeah, heterogeneous catalysts, okay, are used more in bulk chemical industry, like the manufacture of methanol, for example, the manufacture of acetic acid. These are bulk chemicals, or phenol, as you saw a while ago. That's because they can be recycled. Yeah, you produce a chemical, by the way, in bulk amounts. Yeah, and of course that will cost a lot of money. Yeah? If you use a catalyst that you cannot recycle, that will consume a huge amount of money from that chemical industry or that chemical company. Yeah, so it is better if a chemical is produced in large amounts. It is better that the catalyst is reused. Yeah, because that will save will save money, of course, yeah, and it will save the waste as well, yeah. So it will be green from different aspects. Homogeneous catalysts, on the other hand, cannot be recycled, yeah. So homogeneous catalysts cannot be used, therefore, in bulk chemical industry, because if they are used in bulk chemical industry, then that will result in huge amount or huge consumption of money because they cannot be recycled. Yeah. Okay, so that's really the drawback or the point of not using homogeneous catalysts in bulk chemical industry. Homogeneous catalysts, by the way, they are used in pharmaceutical industries, yeah, or the industry of specialty or fine chemicals. But then homogeneous catalysts, because you see a very important feature, as we mentioned, homogeneous catalysts, a very important feature of homogeneous catalysts is the high reaction rate. And a drawback of homogeneous catalysts is the lack of recyclability because they are soluble, right? Okay, so that's really the negative thing about them, yeah. If we can make them separable, then the homogeneous catalyst will combine the features of both, not only homogeneous catalyst, but also heterogeneous catalyst. So the question is, can we make homogeneous catalyst heterogeneous? So the answer is yes, actually, it is possible, yeah, in what's called heterogenization of homogeneous catalyst shown in blue in this slide, yeah. And so heterogenization means, of homogeneous catalyst means, is you make a soluble homogeneous catalyst insoluble, right? A soluble homogeneous catalyst insoluble, and the goal is to make it separable at the end of the reaction or the end of the process, to make it recyclable, therefore. So how can this be done? This is, so you see again, more details is given here. If you make the homogeneous catalyst insoluble, then it separates itself from the reaction mixture. Then we can separate it. Then we can, by filtration, for example, and then we can reuse it, okay, or we can even save it for future use. And a specific example of this is what is shown in front of you, yeah? So you see, the second reactant is an amine. Yeah? Amines are organic bases, and organic bases catalyze different types of reactions, yeah? Okay, so the amine has also a silicon, yeah? Okay, if you take this amine with the silicon, it will definitely dissolve in an organic solvent, yeah? Okay, and if you use it as a catalyst, then you cannot really recover it at the end of the reaction because it will still be soluble in the organic solvent, yeah? But before you do the reaction, if you react it with a silica support, like the first reactant on the left, if you react the amine with this support, it's an inorganic support, yeah? You make an amine product, a product which still has the amine functional group, yeah? But this amine product with the silicon support now is insoluble, which means if you take now this amine with the support and you use it then later in organic reactions, not only it will catalyze the organic reaction, it will be still insoluble in the organic solvent, which means when the reaction is finished, you can separate it. Yeah. That's really the bottom line. So again, this is an example of a method to heterogenize a homogeneous catalyst. This amine is a homogeneous catalyst on the left side. The second reactant is a homogeneous catalyst. If you react it with a silicon or a silica inorganic support, you will make the same amine, but now it's insoluble. If you take this insoluble amine in an organic reaction, it will do the organic reaction, of course, but also at the end of the reaction, it will be insoluble and then we can separate it and then we can recycle it. So this is a combination, therefore, of the features of a homogeneous catalysis or homogeneous catalyst and also heterogeneous catalysis or catalyst. There are different types of catalysts based on the function that they can do, okay? I'm not going to go to the details. There's what's called asymmetric catalysis, a catalyst that produces one enantiomer selectively than another enantiomer. And of course, you remember stereochemistry, yeah? Okay, chiral centers, basically a center or a carbon that is surrounded by 4 different groups. And if that's the case, and if there's only 1 chiral center, there are 2 enantiomers. If there are 2 chiral centers, 4 stereoisomers, and so on. Yeah. Okay. So asymmetric catalysis basically is a catalyst or catalysis that produce 1 enantiomer selectively or 1 stereoisomer selectively. And stereochemistry, by the way, is essential to life. As I said in my organic chemistry lecture, polarity is essential to life because water is essential to life, and water is polar. Stereochemistry is essential to life. Okay, there are some medicines, by the way, which contain chiral centers. Okay, if there is a chiral center, there are 2 enantiomers, right? If the wrong enantiomer, or you remember there's enantiomer A, let's say, and enantiomer B, or if we go back to the previous slide, the left enantiomer and the right enantiomer. If there is a medicine that has a chiral center, then it can exist as the left enantiomer or the right enantiomer. But maybe one enantiomer is good, but the other enantiomer is bad. So if you are given the wrong enantiomer, okay, then that will result in side effects, maybe death. If you're given the right enantiomer, then that will result in curing of the disease. Okay, so why is this stereochemistry important? Because enzymes are site selective in the human body, by the way. The human body itself has sites that accept compounds or medicines that can only accept certain enantiomers, but not the others. Okay, let me give you this very simple example, which is known, I'm sure, to some of you, and I give this as molecule of the day in organic chemistry lectures here, thalidomide. Thalidomide is a compound that's used in Eastern Germany, by the way, a long time ago, like 30 or 40 or 50, actually in the 50s, 60s, yeah, in East Germany for pregnant women to make them get rid of fatigue, you know, tab, yeah, okay. But as you see, thalidomide, the first structure on the top, has a chiral center. The carbon that's connected with nitrogen is chiral. And this chiral center can exist as 2 enantiomers, the R enantiomer and the S enantiomer. But what the problem is, thalidomide before in East Germany a long time ago was prescribed, and it was given as a mixture of 2 enantiomers. Yeah. But one of them is good, the other is bad. The R is good, the S is bad. So as a result of this woman who took the wrong enantiomer, unfortunately, they gave birth to babies with limbs. عارفين؟ يعني للأسف يعني يد يعني قصيرة مثلا، يا أوكي، يد قصيرة if you like، أوكي، رجل قصيرة، يا مشوهين، يا with deformities، yeah. So they gave birth to babies with limbs, yeah, short hands or thin hands, yeah. Short legs or thin legs or deformed, basically, and مشوهين, if you like. Okay, so this is it's remarkable and it's really fascinating because it tells you how important stereochemistry is. Okay, simply because these women take the wrong enantiomer, the result was fatal. Yeah, the result was fatal. Please Google it after the lecture to learn more about thalidomide. And of course, later on, chemists, okay, develop a method to separate the enantiomers, and then the right enantiomer was the drug or the compound or the medicine that was prescribed to women or to patients who needed it. Yeah. So this is, and again, a manifestation of the importance of stereochemistry. And again, we are talking about catalysis, okay, because it's really asymmetric catalyst that can make the production of one enantiomer more than another, and catalysis is a green chemistry principle. So that's the connection. Another type of catalysis is what's called phase transfer catalysis. Okay. We don't have to worry about details again because of the time, but a phase transfer catalyst is a catalyst that has organic and non-organic features. Yeah. So if you like, a catalyst that dissolves in organic solvents and also it dissolves in water. So for it to be able to be of that nature, it should be organic enough to dissolve in organic compounds, which means it should have enough number of carbons, 13 carbon atoms as in the slide. But also it should be water soluble, which means it should contain an ionic bond, yeah, an ion, and a quaternary ammonium salt, for example, an example of an ionic bond for the catalyst to be water soluble. So it has dual nature, therefore. Okay, this is an example. You don't have to worry about the reaction if you don't like these reactions, okay? But this is an addition reaction of alkenes, a reaction of alkenes with carbenes. And if you take basic organic chemistry, I'm sure this brings a bell in your head, the addition reactions of carbenes to alkenes. Yeah. And one example, or one type of carbene is dihalocarbene, like the reaction between this is CHX3 here, and the hydroxide ion. Now the hydroxide ion, by the way, sodium hydroxide, as shown in the equation or the reaction above the bold line, sodium hydroxide is water soluble, yeah? And of course the alkene and the halogen are organic solvent soluble. So they're soluble in the organic solvent. Sodium hydroxide or the hydroxide ion cannot dissolve in the organic solvent, yeah? It's impossible, yeah? Okay, which means the hydroxide ion cannot react with chloroform or with haloform. CHX3 is haloform. So sodium hydroxide must react with haloform in order to make the carbene. But sodium hydroxide cannot react with haloform if they are not in the same solvent, yeah? Because sodium hydroxide is water soluble, haloform is organic solvent solubles. But if we add R4N plus X minus, an example of a phase transfer catalyst, to the reaction mixture R4NX minus, this is organic and aqueous, which means it will dissolve in both organic solvent and water, yeah? Which means it can dissolve in water, and when it goes to the water layer, it will take sodium hydroxide or the hydroxide ion from the aqueous layer to the organic layer. So it takes it up to the organic layer. When the phase transfer catalyst or the ammonium ion takes the hydroxide ion from the aqueous layer to the organic layer, then hydroxide ion will be able to react with CHX3 in order to make the carbene. And then when the carbene is made, then it can react with the alkene, yeah? Okay, so you see, the phase transfer catalyst goes from the organic solvent to the water layer. It takes the hydroxide ion to make it react with CHX3, and the reaction will go, and it does this millions of times until the reaction is completed. This is an example of a phase transfer catalysis where a material like this ammonium ion dissolves in both solvents, organic and water, and that it takes the inorganic ion, which is the hydroxide ion, from the water layer to the organic layer, facilitating the organic. There is biocatalysts, of course, and biocatalysts are basically enzymes, and enzymes are basically, as the biologists will now tell me, or the chemical biologist or the biological chemist or the chemist, yeah, will tell me enzymes are amino acids, yeah. Okay, so biocatalysts are basically amino acids, and they are very important nowadays, by the way. And of course, enzymes or biocatalysis or biocatalysts are very important to life, yeah. Why are biocatalysts important? They are, of course, essentially amino acids. And this is the general structure of amino acids. And if you look at the general structure of amino acids, you will see that they contain a carboxylic acid unit and an amine unit. Carboxylic acid, this means that amino acids are acidic in nature. Okay, amino acids contain also nitrogen or an amine functional group, which means that nitrogen has a lone pair, which means that amino acids are basic. That's because the nitrogen has a lone pair. Remember, organic bases are materials that contain a lone pair. Therefore, amino acids have dual catalysis, acidic because they contain a carboxylic acid, and basic also because they contain an amine function. Some green features of enzymes, by the way, or biocatalysts, okay, they are really very, very efficient. throughput means the conversion, faster throughput means conversion of a reactant, by the way, into a product, of course, with the aid of a catalyst or biocatalyst. Yeah. So if they are efficient, they are highly selective enzymes also, or biocatalysts. They are water based, so they are water soluble, which means reactions that are based in water are then possible, which means you don't have to use an organic solvent. Remember, yeah, solvents, okay, the use of volatile organic solvents is not recommended. Yeah, so this will allow, a biocatalyst can allow the use of water, which is green. There are limitations, okay, to them, which means one of them is the lack of stability under certain conditions. Yeah, okay, and also they can be expensive, like as in the case of single enzymes. Yeah. Photocatalysts are basically catalysis that use light, if you like, or use the sunlight, for example, to do chemical reactions or transformations. Okay, the concept of photocatalysis is similar to Einstein's finding, by the way. A light hits a metal surface, and then electrons are emitted or photons are emitted, and of course, a certain amount of light, by the way, that is required for electrons or for photons to be emitted from a metal surface, and that amount of light or energy is called threshold energy, if you remember, yeah? Or threshold frequency, because light is characterized by frequency and wavelength. Yeah, it's basically Einstein's idea, similar to that. So basically, electrons or photons are now, when emitted from a metal surface, they are used to initiate chemical reactions or to do a certain type of degradation, yeah, like in waste treatment. Now we reach a very important principle of green chemistry, which is solvents. Yeah, this is separate green chemistry principle on its own. Yeah, so green chemistry aims at using safe solvents or safer solvents, if you remember the 12 principles of green chemistry, and auxiliaries. Yeah, okay. So we need first to describe a solvent. So what is a solvent? A solvent basically is a substance that dissolves a solute, and when it does so, a solution is formed. Yeah, a solvent dissolves a solute to make a solution. And solvents are used generally or usually in chemical reactions, but not always. And when, of course, they are used in chemical reactions because they make, reactants soluble. Okay, so that's an important feature. They solubilize or they homogenize reaction mixtures by dissolving reactants. Not only they dissolve reactants, they also dissolve intermediates, by the way, and products. Yeah. And because of this, the reaction is facilitated. And because of the homogenization of the reaction mixture, whether it's reactants, intermediates, or even products, the reaction is actually facilitated. Yeah. Okay, or the rate is enhanced. Yeah, so the reaction rate is enhanced, okay, as a result of using solvents. Okay, and solvents also, they can absorb heat. Yeah, so they can act as a heat sink, if you like. Yeah, heat sink. Yeah, and if they absorb heat, then they can promote reactions which produce heat. As you know, some chemical reactions produce heat. Yeah. Okay, and some chemical reactions absorb heat. Yeah. So for those reactions that absorb heat, yeah, if the solvent absorbs heat, okay, the reaction will be driven to the forward direction, if you like. Yeah. So that's why this is another method or mechanism by which solvents speed up or facilitate reactions. Yeah. Not only they are used in reactions, they are also used in workup procedures, like extraction, and also they are used in purification, like distillation and like in chromatography and recrystallization. Yeah. So solvents are used really in different stages of chemical reactions. Yeah. But the question is now, do we need a solvent, or do we always need a solvent? Well, the answer is no. We don't always need solvents. Some reactions can be run under solvent-free conditions. Okay, so an example is Qamna. Okay, so where a reaction does not require a solvent. So the answer is no. It's not always that reactions require solvents. Yeah. So what is the problem with the solvent if we use it? Yeah. So why do we have to get rid of the solvent? Yeah. The solvent is good, right? Because it dissolves reactants. Yeah. It speeds up the chemical reaction. It acts as a heat sink, and therefore it can accelerate chemical reactions or facilitate them. So what's their problem? Well, their problem is that some solvents are volatile organic compounds. Yeah. So if you're a biological chemist or a biological scientist or a biologist or environmental scientist, yeah, you are familiar with what's called the VOC, okay, or the volatile organic compounds. Volatile organic compounds are compounds that are emitted into the atmosphere, and they can affect the atmosphere adversely. They have negative impact, obviously, like low-level ozone, and they can make smoke. They can affect health, okay, like they can irritate the human body, the eyes, the skin. They can cause all kinds of health problems like headaches, fatigue, and so on, dizziness, and nausea. Okay, so therefore, if we have to use an organic solvent, and if the organic solvent is volatile, then we try to minimize it, okay, or we try to avoid it if we can. So how can we avoid volatile organic compounds, which are a problem? This is an environmental issue, by the way. So how can we avoid them? Well, the best strategy always is not to use a solvent at all. Yeah. So not to use solvent at all. Yeah. To start with, if we can do a chemical reaction without a solvent, then this is really the way to go. Okay. And we'll talk about conditions for that. Yeah. How can certain reactions take place without a solvent? Okay. So this is really the best approach, because then you can avoid solvents totally. The second approach, if we have to use a solvent, then it is better that the solvent is non-volatile. And this way we can reduce the problem of the VOC, the volatile organic compounds. Okay. Another method is to use water-based processes or reactions that employ water as a solvent. Yeah. And of course, water is green. Yeah. Okay. A fourth one, or a fourth strategy, is to use ionic liquids or supercritical fluids, and also fluorous biphasic solvents. I'm not going to talk about the details of all of these. I will just talk about some notes about two selected ones. Yeah. So the solvent-free processes, the reactions that can go without a solvent, they must have requirements. Yeah. And one requirement is that one reactant should be a liquid or a semi-liquid. One of them should be a liquid or a semi-liquid, or if you like, one of them is miscible or soluble in another, or at least partially soluble. Yeah. Okay. So if that's the case, then the reaction can be run without a solvent, because one of them will act as a solvent, if you like. Yeah. So there's then no need. There's then no need for a solvent. This is an example of a chemical process, and please write down this reference. Yeah. J. Chem. Soc. Berk. Whatever. Yeah. The details of the reference if you want to read the paper. This is an example of a chemical process that does not involve or employ any solvent at all. These two compounds, the two reactants on the left, okay, they are mixed with sodium hydroxide, and they are ground, by the way. يعني ينطحنوا, if you like. You can grind them in using porcelain and a mortar. Yeah, you get the product, and then the same thing, you add another reactant, and again you grind, okay, the mixture together. You get another product, and then you add another reactant, yeah, and then you grind. There's no waste, okay, and only you get the product which is a solid. This is remarkable, and if you want the details, please check out the reference. And this is an example of a process or a synthetic route that does not employ a solvent. Another strategy for or green solvents, if you like, is supercritical fluids. And supercritical fluids are basically compounds or fluids or liquids or solvents that can exist above their critical pressure and critical temperature. Okay, this is a diagram in the front of you, so you can read it, you can look at it. Yeah, okay. There's engineering here. There's also science. There's chemistry, obviously here. So details will not be discussed because of the complexity of this topic. But for us, for us as chemists or green scientists, supercritical fluids can be used because when they are at the supercritical stage or after the critical point, basically, their behavior is different, yeah. So they can have modified properties, if you like density and viscosity, yeah. So as the temperature increases, the compound becomes less dense. If the pressure increases, it becomes more dense, yeah. So properties can be different, okay, of supercritical fluids, okay, different from the solvent or the compound when it is under normal conditions, yeah. If it's under supercritical conditions, then maybe it can facilitate, you know, reactions, or maybe it can accelerate or promote reactions that are difficult otherwise, or reactions maybe that are done using volatile organic compounds. The idea is to avoid these volatile. So achieving the critical point, remember the critical point is the point between the three phases or states of matter, yeah, gas, liquid, and solid, at the triple point here. At the critical point, then the liquid can behave in a certain way which can be useful, okay, but not always, yeah. Okay, if we take, for example, if we look at this table, you will see how difficult it is to achieve the supercritical state of any solvent, yeah. If you take ammonia, for example, it requires 132 degrees Celsius, whereas carbon dioxide, 31 degrees Celsius. Water, for example, 374 degrees Celsius, which means water is very difficult to achieve relative to carbon dioxide. So that's why supercritical carbon dioxide is used more than supercritical water, okay, for the reasons that are just mentioned, is that the supercritical conditions of carbon dioxide are accessible. The temperature is not high and the pressure is not high, so you can achieve supercritical carbon dioxide, SCCO2. So, and why do we use carbon dioxide anyway? Well, that's because carbon dioxide can be used in extraction, by the way. It can extract coffee from, or caffeine from coffee. It can extract certain ingredients even from natural sources, like in food industry, flavor, fragrances, perfumery, for example, yeah, okay? So it's used mainly as extraction, and its removal is very easy, by the way. That's because carbon dioxide is a gas. If you bring it back to normal, it's a gas, so it will evaporate, yeah. But then you may see it's a greenhouse gas. Well, that's correct, okay? Now, when this procedure is done, it has to be done, or its engineering has to be done carefully so that the carbon dioxide released by a certain process is used in an extraction. So basically, it's recycled. And then when carbon dioxide is brought to normal, it's not allowed to enter the atmosphere. So it's forced to enter pipelines or pipes that will be, through which the carbon dioxide will go, and then it can be recycled carbon dioxide, but not really emitted into the atmosphere. So the net global warming is really zero. Okay, so this is just to make it clear. So the point here is that carbon dioxide is easy to achieve. If you bring it back to room temperature, it's a vapor, so it can evaporate by itself. Yeah. But again, the engineering of the process, whether it's chemical or engineering, it has to be carefully managed so that carbon dioxide that's produced is not allowed to enter the atmosphere. So there is no net global warming. So the advantages of supercritical carbon dioxide, it is non-toxic, of course. Yeah, it is easy to achieve as supercritical fluid. It's easy to remove because carbon dioxide is a gas to start with. Yeah. Okay, a disadvantage. Okay, it's reactive. Yeah, if you use SCCO2 in chemical reactions, it's not a good idea because carbon dioxide is an electrophile. So I don't have the time to talk about the chemistry But carbon dioxide is an electrophile. This carbon in CO2 is electrophilic because of inductive effect and resonance, by the way, which means carbon, because it's electrophilic, it can be attacked by nucleophiles, which means if you use supercritical carbon dioxide in reactions that have nucleophiles, such as grignards and organolithiums, for example, yeah, then these reagents, which are used for a certain chemical purpose, will now attack carbon dioxide. So they will react with it. So that's why it's not a good idea to use supercritical carbon dioxide in chemical reactions that have nucleophiles, because carbon dioxide itself is an electrophile. What about water? Well, water as a solvent is actually great, but water as a supercritical fluid is really a bad idea to use as a solvent, because SC water or supercritical water is a very harsh oxidant, by the way. If you use SCH2O in chemical reactions, you know what will happen? It will simply destroy the reactions totally. It will destroy the reactants. It will simply oxidize them to carbon dioxide and water. It's not a good idea at all. So that's why then SCH2O or supercritical water is definitely not good as a solvent, but it is good to treat waste, by the way. So that's why it's used in waste treatment. And that's why this technology that's called SCWO or supercritical water oxidation is implemented, because SCWO allows degradation of organic waste into carbon dioxide and water. It is used as waste treatment, but only as supercritical, by the way. Water at normal conditions is good as a solvent, yeah, which means room temperature, atmospheric pressure. Water, the normal water that we use in daily life, yeah, this is good as a solvent, by the way, yeah, okay. But the supercritical water is not good as a solvent, okay? Because supercritical water as a solvent, as I mentioned, this destroys organic compounds by oxidizing them to carbon dioxide and water. Yeah. So water as a solvent under normal conditions is green. Supercritical water is good not for chemical reactions, but for waste treatment. Water is good, by the way, as a solvent. It can enhance certain chemical reactions. This is an example. Again, you don't have to worry about the details, but look at the relative rate. You will be amazed. The rate of the reaction in isooctane as a solvent is 1, in methanol is 12.5, water 740. So look at the reaction in water is 740 times faster than when it is in an organic solvent like isooctane. Why is that so? This is because of what's called the hydrophobic effect. So if you do the reaction in the presence of water or in water, water will not dissolve organic compounds or organic reactants. Remember, R1 plus R2, yeah, in water. So R1 and R2 will not be dissolved in water. They will be together. And they will be together because they are not soluble in water. And that's because they are together, now they will collide more. They will encounter each other more. If they collide more, then the reaction will be faster. Yeah? Because the collisions will be more. Remember, every reaction begins with a collision. Yeah? Okay, the reactants will collide if they see each other. They meet each other, and they meet each other when they are together. And they'll be together if they are not soluble in water. Yeah? Okay, so in this specific reaction, that is the case. Okay, organic compounds are clustered together in the form of drops, which means the chances of their collisions is now higher, and that's why the reaction is now much faster than an organic solvent. If you look at the reaction rate in the presence of water and now using an additive such as lithium chloride, the reaction is even faster, 1,800. This is amazing and it is remarkable. It's even faster than in water itself. That's because when you add lithium chloride, now this will polarize the reaction medium. It will polarize the lithium chloride because it has lithium cation, by the way, and the chloride ion Cl-, yeah, okay, it will polarize the reaction medium, and by this polarization, water will react accordingly, will be attracted to the polar ions, and if it's attracted to the polar ions, the pressure inside the reaction flask or inside the reaction will be higher, and if the pressure is higher and the volume is reduced, the chances of collisions is much, much higher. And that's why the reaction rate is further enhanced if lithium fluoride is added to an organic reaction that has already water. And of course, this does not apply to every reaction. Please remember, this is only one example of a reaction where water works as a solvent. Yeah, but this does not mean that water can work as a solvent in all organic reactions. That's not the case. So is there a green solvent in general? The answer is no. So how can we judge if a solvent is perfect or not? Well, that will depend on the chemical reaction itself. So there's no such thing as a perfect solvent, by the way. There's no such thing as a totally green solvent, by the way. Yeah? Okay, unless it's water. Yeah? But then the reaction has to work obviously, or to proceed in water if water is to be used. Yeah. So the greenness, okay, it's combination of all kinds of properties, okay, the hazardousness, the toxicity, and then the volatility later on, which will depend on the boiling point, obviously, and the flash point. And of course, the solvent should not persist in the environment, yeah, okay. And also the details of the reaction, okay, like the preparation method, how can we, if the solvent is green, how can we reuse it? How can we recover it at the end of the reaction? All of these considerations will determine whether a reaction is appropriate or suitable as a green solvent in a specific chemical reaction. So the guidelines or the judgment is based on these criteria, and there's no blind rule, if you like, that will dictate us to say or judge that this solvent is green and it is green always. Yeah. We just have to exercise caution and be careful and be vigilant, and we need to examine all kinds of properties, the solvation properties, the effect of the solvent during the reaction, the volatility of the solvent, the toxicity of the solvent, the hazardousness, and the recovery at the end, and considerations of that type before we can choose or determine the suitability of the solvent. Now we go to a very important principle of green chemistry, which is the use of renewable resources. Remember, if you remember the design for degradation, one rule says if renewable resources are used, then the compound is degradable because it's made from natural sources or natural materials. Yeah. So that's why this is actually a green chemistry principle. Yeah. When we speak of renewable resources, we speak of biomass. When we speak of biomass, we are talking about non-animal renewable resources, basically trees, if you like, yeah, or wood, yeah, trees or wood, things like that. Yeah, this is basically called biomass. Biomass is used, by the way, to manufacture fuel, you know, for cars, you know, trains, vehicles, airplanes, and so on. And also biomass is used to manufacture chemicals. But why do we use biomass, or why do we use renewable resources? Well, the answer is, I'm sure, is known to you already. That's because now we use oil, or if you like, fuel that's based on fossil resources, yeah, or fossil fuels, if you like. And fossil fuels, by the way, they have all kinds of problems, yeah. Okay, so we want to reduce, yeah, the reliance on fossil fuels. Okay, why do we have to do this? Because fossil fuels are ending, yeah. So as you know, they will not be here forever. So they're actually ending. We will reach a time stage, but there's no fossil fuels anymore. So that's why we should not rely on fossil fuels heavily or primarily. So we should look or seek other alternatives like renewable resources. The other problem with fossil fuels is that they produce materials that are harmful to the environment, which can affect adversely climate change pollution and global warming, like the emission of greenhouse gases, for example. So this is another problem. So that's why then scientists and governments, okay, now seek alternative routes or methods to fossil fuel-based sources. So the idea is to shift from fossil fuels and to seek renewable resources like biomass, okay? And also wind, and also water, as you know, solar energy, nuclear, and you know, there are all kinds of techniques or methods or technologies which can be used to make fuel and also to manufacture chemicals. Okay, biomass can be used to manufacture fuel and chemicals. So I will explain, yeah, but also not in details because again, this is a little bit beyond the time limit of the lecture. Yeah? Okay, so biomass generally consists of starch and cellulose. Yeah, okay, so starch and cellulose. If you burn wood or trees, you get carbon dioxide and water. So this is the burning process. And when you burn it, you can get fuel, by the way, or you can get other types of products because the conversion of biomass can vary depending on the temperature. So this chart shows how biomass can be converted. If you burn it, you get heat. Yeah, heat is used, by the way, in the cold winter, especially in Europe. Yeah, so they يحرقوا الخشب. Yeah, okay, للتسخين للتدفئة, if you like. Okay. Now, other processes can be used like thermolysis, pyrolysis, and that will depend on the temperature that's used, and that will determine the type of product. Yeah. Okay. If gasification of biomass is used, so gases are produced, and if gases are produced, then what's called synthesis gases can be converted into different types of products, whether heating or even for other products such as biofuel, for example. Yeah. So we talked about burning, thermolysis, and pyrolysis, which will depend on the temperature that's used. If we gasify biomass, then synthesis gas is produced, like carbon monoxide and hydrogen. And there's also fermentation, like the manufacture of bioethanol or biofuels. Yeah, here we touch biofuels in general. Yeah. Okay, speaking of biofuels, of course, you're familiar with bioethanol and the history of bioethanol, and that's the fermentation of glucose, basically, or glucose-based crops, okay, such as sugar canes, okay, with the help of yeast, yeah. And of course, there have been developments in this. This was in this technology, which was started with Brazil, by the way, and then later on the US. And there have been developments, you know, like different generations of the production of bioethanol. Okay, there were limitations of the first generation approach, that specific types of sugars were only converted, but then modern methods employ other types of sugars as well. Yeah, and even different or modern additions or techniques in the manufacture of bioethanol. So bioethanol here is an example of a biofuel or a fuel that can be made or manufactured from renewable resources. Okay, and this will be could be an alternative to oil or fossil-based fuel. There is also biodiesel, which is made from oil also, or vegetable oils, if you like. And again, this was found by Rudolf Diesel, and that's why it's called diesel here. Okay, and you see, if you recall, okay, from your basic biology, that different plants have different oils, you know, or fatty acids, for example. Yeah, you have like soybean, sunflower, as in the table that's shown, palm trees, and so on, and the different types of fatty acids that are contained in them. Yeah. So these in the box here now, different types of fatty acids, and please remember that vegetable oils are basically triglycerides. Yeah, triglycerides, which means triester. So you see in the chemical equation, which is shown in front of you, there's a triglyceride. This is basically a vegetable oil, if you like. So it's a triester or a triglyceride, and R and R1 and R2 and R3, they could be any of these chains in palmitic acid, stearic acid, and urosic acid, and so on. Yeah? They could be the same, they could be different. Yeah, usually they are the same. Yeah, so if you take an oil or triglyceride from vegetable oil, which is a renewable resource, yeah, and then you break the ester bonds. Yeah, so remember esters, if you recall organic chemistry, esters can undergo hydrolysis. And if esters undergo hydrolysis, then carboxylic acids and alcohols are obtained. Yeah. And if carboxylic acids and alcohols are obtained, then all carboxylic acids in the products can be further esterified. Which means if you take the triglyceride on the left side of the chemical equation in front of you, and you hydrolyze it with an acid or a base, then the corresponding carboxylic acids will be obtained. So basically, oxygen-carbon bonds will be broken. You make carboxylic acids and also the alcohol. And the alcohol that's produced is glycerol. So glycerol and 3 carboxylic acids, not these ones, by the way, 3 carboxylic acids will be obtained. But then if you react the 3 carboxylic acids with an alcohol, ROH, you make new esters. And these new esters are the biodiesel, by the way. Yeah? So biodiesel is basically new esters that are obtained by hydrolysis and trans-esterification or another esterification of triglycerides, which are basically vegetable oils. Remember, you need an acid or a base and an alcohol in order to do the 2 steps. Okay, so biodiesel is basically new esters from triglyceride. That's the bottom line. And of course, biofuels. Okay, yes, they are good. Okay, yes, they can provide a green alternative to fossil-based fuels. Yes, this is beautiful. This is nice and great, but they have disadvantages. And as you can imagine, yeah, if we take trees, yeah, and if we take wood or biomass, this means that we actually contribute to cutting of trees. Yeah? So basically, destruction of lands, if you like. Yeah. So destruction of lands or cutting of trees will be a consequence of the reliance of biofuel, the heavy reliance. Yeah. And also, there will be shortages in food. Yeah. So if there is a conversion of biomass into biofuel, okay, food will be less. Yeah. And if food is less, by the way, then prices will go high. Yeah. So this will contribute to the rise in food prices and, of course, food availability. So, but there are solutions to this, and that's to not to heavily use biomass or use plants, if you like, or trees, but to use algae, for example. Yeah. Okay. So this offers a modern alternative to the use of the traditional biomass in the manufacture of fuel. So that's an advance, if you like. Yeah. In addition to biomass, we could also use solar power in order to generate electricity. Yeah? So remember, we are talking, okay, so solar power, we can get heat and electricity from. So again, this will provide an alternative to the use of fossil fuels. Yeah? We can use wind turbines, yeah, to generate electricity again, and you see them now in the far, you see them typically in Europe, yeah, in the Netherlands, for example. Yeah? So it's a modern method for generation of electricity from a renewable resource, environmentally friendly. Although a drawback will be the disturbance of birds, for example, yeah, or civilized lands. We can also use hydroelectricity or electricity that's used that's generated as a result of flow of water. Yeah, so this is also a nice and a green method or alternative to the use of fossil-based fuels. Fuel cells are used to make electricity, by the way, also. Okay, again, another way to make energy, electricity from renewable resources. So basically, it employs hydrogen and oxygen in an electrochemical cell. Yeah. So anode, where the oxidation takes place, cathode, where the reduction takes place. Electricity is generated in the electrochemical cell, and the only byproduct, by the way, is water. It's a green, definitely a green alternative for the generation of electricity. We mentioned also that chemical, not only fuel can be obtained from renewable resources, also chemicals can be obtained. For example, we mentioned oil has fatty acids, remember? Okay, like balsamic acid and so on. These fatty acids, they contain carboxylic acid, and carboxylic acids are converted into other functional groups, yeah. So fatty acids can be converted to esters, and this will give us perfumes, yeah. Fatty acids can be converted into metal carboxylates. This is soap, sabun, yeah, if you want, yeah. Fatty acids can be converted into quaternary ammonium salts, and this is phase transfer catalyst. Remember the time of catalyst, yeah. Fatty acids can be converted to alkenes, and alkenes are used as in the manufacture of polymers, yeah. And fatty acids can be converted into other types of compounds, which can be of industrial use, yeah. This is an example of a fatty acid that's used to make other compounds from it, like orotic acid. If you do amidation, you get anti-slip agent. If you do the left reaction here, reduction, you get this compound, which is very important for certain applications. If you do the alkene reduction, okay, you get a compound for BVC, anti-blocking application, and so on. Yeah. Synthesis gas can be obtained from biomass. So biomass, if you burn it, by the way, if you gasify it, you get synthesis gas, carbon monoxide and hydrogen. This is synthesis gas. And synthesis gas or syngas economy depend on these two materials, carbon monoxide and hydrogen, from which all kinds of materials can be obtained, like esters, you know, gasoline, plastic, or polymers, all kinds of industrial chemicals that are of important human use. The last aspect here is the chemistry of explosives, yeah. Okay, so, and the role of green chemistry in the chemistry of explosives. And again, I'm not going to the details of this, but this figure shows you examples of compounds that can explode. Explosives, for example, like TNT, nitroglycerine, acetylene peroxide, that's used in bombings, you know, like HMX, DETN, RDX, and so on. Okay, all of these are organic compounds, by the way, and if you pay attention to their bonding, you will see they contain nitrogen, and nitrogen-oxygen bonds, yeah, or oxygen-oxygen bonds, yeah. So what's the point here? The point here is that these explosives, they contain certain bonding patterns that can make these explosives explode. So for example, the ONO2 bonding pattern is really what makes trinitroglycerine explode. It is the oxygen-oxygen bond in acetone peroxide what makes acetone peroxide explode. This is used in London bombing, by the way, because the oxygen-oxygen bond is very weak, yeah? Okay, and this bonding pattern in other compounds is what make these bonds susceptible to impact and heat, and therefore they can explode. Now, what's the point here? Well, the point here, we can carefully limit the manufacture of these chemicals, okay, because we want to avoid their possibility of explosion. So green chemistry should help, therefore, stopping or reducing the chances of these chemicals reaching the hands of terrorists. In other words, green chemistry can help reduce the terrorist attacks. By what? How do we do this? Well, by designing safe chemicals, by not allowing the synthesis of weak bonds and therefore explosive bonds, yeah, or certain bonding patterns that can allow explosion, like in TNT, for example, or RDX and so on, yeah. We try to make synthetic routes as safe as possible, and we try to reduce the accumulation of hazardous materials, and especially we want to stop reaching of these hazardous chemicals or these hazardous materials. We want to stop them from reaching the hands of terrorists, like, you know, like sulfuric acid, for example, hydrocyanic acid, or even ammonium nitrate, as you heard in the Lebanon bombing, yeah, although it's used as a fertilizer. But again, care has to be exercised in storage of these materials. Care has to be exercised by not allowing the easy access to these chemicals to terrorists, yeah, okay, and therefore we can stop or at least reduce terrorism. So we have green chemistry has really a very important role in the minimization of terrorism. And of course, when it comes to analytical chemistry, detection is also very important. Yeah. So to conclude here, this is the end of the lecture now. Green chemistry is a practice of chemistry whose aim is maximization of benefit, profit, if you like, and also at the same time, minimization of negative impact. Sustainability is linked with green chemistry, by the way. Sustainability is extremely important. Istidama, if you want, again, okay, not only we meet the needs of the current generation, but also we should not destroy the needs or the necessities of the future generation. Again, you don't want a method or a strategy that works very well now, but it may not work 5 years from now. Prevention as a green chemistry principle is the best strategy for the minimization of waste. Green synthesis is the one of the shortest route. Okay, remember, we want to minimize chemicals, we want to minimize materials, we want to minimize substances, we want to minimize solvents, we want to minimize steps, we want to minimize energy, we want to minimize the consumption of money, and so on. The best reactions are the ones that are of total percent atomic economy, as we discussed. The reactions that employ catalysis because they can reduce waste. The best synthesis or reaction is the one that does not have a solvent at all, or a solvent that is environmentally benign, like water, or a solvent that is not a VOC or a volatile organic compound. Catalysis really is the way forward in any chemical synthesis, by the way, because catalysts are used in small amounts, therefore waste is reduced, money is reduced, and materials are also reduced. We want to reduce the reliance or dependence on fossil fuels by seeking renewable resources like biofuel, okay, for the manufacture of fuel and chemicals, and also by looking at solar and energy and other types of technologies to manufacture electricity. Green chemistry has a very important role also, as we mentioned a while ago, into mitigating terrorism. And I hope this lecture has been green. Thank you very much for your attention.